Hello, my name is Stephen Price, and I'm a PhD student at Worcester Polytechnic Institute. At WPI, my research is positioned at the intersection of material science and machine learning. With a background in computer science, I strive to advance material science research by employing a data-driven perspective that can uncover insights and relationships otherwise difficult to determine through traditional approaches. Today, I'll be discussing my research predicting the bead shape in wire arc-directed energy deposition, or wire arc DED for short. First, what is wire arc DED? It's an additive manufacturing technique that uses an electric arc such as this to melt and deposit a thin wire. This process deposits a wire layer by layer, much like a regular 3D printer, except using metal. Some key advantages compared to traditional manufacturing include reduced material waste, lower production costs, higher energy efficiency, and rapid prototyping capabilities for accelerated design refinement. As a new technology that has only gained traction recently, there is still room to optimize manufacturing conditions, like selecting the ideal processing parameters for a given set of materials. My research has focused on inserting machine learning into this process, enabling us to model, predict, and optimize these manufacturing conditions. To accomplish this, we analyzed how these parameters impacted the bead shape of single-layer prints. So why is this important? Understanding and controlling bead geometry is critical in wire arc DED for ensuring structural integrity, reducing porosity, and minimizing material waste. An optimal bead maximizes the width-to-height ratio, maintains a steady surface profile, and avoids overhangs or muffin tops that compromise part quality. Precise bead shape control is also essential for planning paths and layer spacing, as gaps or excessive overlap can weaken structural integrity. Past work has utilized machine learning to support the optimization of processing parameters with respect to bead shape. However, these studies were limited by the size of their data, often having between 16 and 75 samples. Additionally, these studies only evaluated conditions for a single material, which makes it difficult to apply to others. For my research, we sought to expand on previous studies with a more data-driven approach by collecting the largest and first multi-material dataset relating processing parameters to bead shape. This dataset contained 553 unique parameter combinations across 5 wires and 4 substrates using a design of experiment specifically tailored for machine learning. For each combination of parameters, we deposited a 6-inch single-layer bead and used a 3D scanner to extract relevant features. These included the industry standard width and height, as well as 2 novel metrics, width variance and height variance. Initial models using processing parameters and materials yielded reasonably high performance. We improved these results further through novel feature engineering. For example, rather than telling a model a material was 4140 steel, we gave the model the percentage of each element such as carbon, nickel, or iron that was present in 4140 steel. In addition to providing more information on material similarities for improved learning, this also enabled predictions on unseen materials, allowing research to be utilized across multiple projects. Many assume that a neural network will always be the highest performing model. However, in fields such as material science, where there are not thousands of samples readily available, this is not always the case. Thus, we evaluated many model architectures, including linear, nonlinear, and ensemble models, in addition to a neural network. As a result, we discovered that the neural network was not the best model for any of the features that we predicted. Polynomial regression performed the best for width and height, scoring an R-squared of 0.97 and 0.99 respectively. Random forest performed the best for width variance with an R-squared of 0.86 and height variance with an R-squared of 0.67. With such a high-performing model on a dataset specifically designed to encompass the entire parameter space, we can confidently use this model to predict the bead shape of every parameter combination on these materials. For example, the maximum width-to-height ratio on our experimental data was 4.54. However, using a trained model to search for optimal conditions, we hypothesized that using a slightly different set of parameters will result in a larger ratio. As a result, we can exceed the local maximum in the data with a globally optimal set of parameters. As of now, our collected data and preliminary analysis have been published, and the remainder of the work, including the feature engineering and model performance results, are currently under peer review for publication. To summarize the accomplishments of this research so far, we have, to the best of our knowledge, collected the largest dataset relating parameter combinations to bead shape, collected the first bead shape dataset with multiple materials, trained the highest performing model on external validation sets for width and height, trained the first models that can be used to predict bead shape on multiple materials, even those that were not included in the dataset, and introduced novel metrics to develop a more informed optimization process. Now, why does this matter? At the start of every project, researchers will print a series of test beads to decide which set of parameters they use, especially when new materials are introduced. With this model, we can reduce or eliminate the number of samples required and ensure finding a globally optimal set. This reduces the cost and lead time of preliminary testing. Additionally, with information on the bead shape every parameter combination would yield, we'll be able to dynamically change our parameters throughout a print to tailor deposition to specific regions of the part. Moving forward, we seek to extend upon this work through a few key steps. First, we'll introduce thermophysical properties in addition to chemical properties as a part of the feature engineering process. Next, we'll extend these models further to predict surface profiles in 2 and 3 dimensions instead of simply predicting the industry standard width and height. This will give us more information, enabling a more precise optimization process. Lastly, we will directly integrate this work into the manufacturing process to improve part quality and reduce waste.